Knowing Nyquist stability theorem, although I didn't explain well enough, um, the next thing you need to know in order to really understand what is stability, okay, and how to find stability, you have to first know how to find the gain and phase. And the following this video will talk about just introduction of gain and phase, the true meaning of it, and then next video I'll just go into the details of it. So in this video I'll just start off with this one, and then along the way I'll just
Now I covered this in the first few minutes of the introduction Bode plots video, but I'll sum it up here for completeness. Let me draw a linear time invariant system, G of S, which acts on an input and generates an output. When a sine wave is played through it, it's distorted based on the properties of G of S. That distortion for an LTI system comes in two ways. The magnitude of the system can change, and the phase of the signal can change. Gain is the proportion of the magnitude of the output to the magnitude of the input at steady state.
So this is actually the gain shift. Okay, you increases the gain. Okay.
If the output is twice as high as the input, we'd say that this system has a gain of 2 because it multiplied the input by 2. And similarly, phase is the shift of the signal measured in angle, or just fractions of a wavelength. So in this case, this signal is shifted a quarter of a wavelength, which is minus pi over 2 radians, or
As you can see, it's phase shift is as well we have tell you earlier. So this is the phase shift.
minus 90 degrees. Sign convention is such that a delay in the signal is a negative phase shift. So the output for a single input frequency is a combination of gain and phase shift.
And also why is it negative is because your yellow color is actually lagging behind the red color by minus 90 degrees. Okay. So because you start the red one is you start here, or however you have you took another you took a more time to actually start up from here. Eh? Where is the starting up? Sorry. Oh yeah, okay. So you took a more slightly more time to start up from here. So the red color start from here, the yellow color starts from here, and then so it's a little phase shift. So the yellow color has a delay like in a certain sense. So let's continue.
Shift. But here's the thing. The gain and phase can be different at different frequencies, and they usually are. And this is exactly what a Bode plot shows you. It shows you the gain and phase of a system across the entire frequency spectrum. So when we're talking about how much gain and phase margin we have, we need to consider all of the frequencies. And
the Bode plot is actually to look at the gain and the phase. So till now, if you don't know, it's okay. So let's continue.
That's one of the reasons Bode plots are so popular for this. Now there's one other thing I want to mention on gain. The word gain is used all the time to indicate a scaling term. Now while this makes some sense, it can be confusing at first to someone trying to learn gain margin. Let's see if I can clear it up with a series of simple diagrams. Let's say G of S equals 5. Now it's obvious that the gain is 5 at all frequencies because you're just multiplying the input by 5. But if I had a scaling term here of 2, then I would say that I've increased the gain by a factor of 2, and that the system gain is now 10. However, let's look at a slightly more complex system. The gain of the top path is 5, and the gain of the bottom half is 3. Now the total system gain is 5 plus 3, or 8. However, if I increase the gain of the top path only by 2, it doesn't increase the system gain by 2. If we did want to increase the system gain by 2, we'd have to move the block forward so that it gets applied to all paths. But then if I add feedback into this system, this gain no longer affects the whole system equally again. The point that I'm trying to make is that once you determine the gain margin of your system, you need to understand exactly which scaling terms can be increased to take advantage of that margin.
So gain margin is a little abstract, but as you can see, the different gains you have, okay, is all dependable on the position of your multiplier or whatsoever. So it is it is that. So you have to really understand. So the gain margin is the gain isn't just scaling, although it's scaling itself, but in terms of the block diagrams, you are talking about systems. So which block affects the gain pretty much. That's the thing. And apparently in the gain margin, later he'll explain. So hold on a while. I think never mind. We continue first.
It's not just any path in your system. I'll try to be explicit about which gain I'm talking about for the rest of this video. especially when I'm talking about the open loop system versus the closed loop system. Okay, now let's talk about margin. Margin is the extra amount of something that you can use in case you need it. For example, when we're talking gain and phase margin, we're referring to the extra gain or phase in the system that we can use before the system starts to oscillate and go unstable.
So let me repeat again. So the gain and the phase is margin is extra amount of something, okay, phase or a certain magnitude, in order to so the more the amount of margins you have, the more um the more safer you are. In other words, the margin is like a, let's say you have a, this is the margin, okay, and then if let's say this is a scale line, okay, you can be here, you can be here, but make sure you don't cross this margin. So this is the thing that it's saying. So if you are here, this thing, this amount of thing is actually the, so this is the so-called the limit, while this is the margin, I would say. So the if let's say your system, in other words, is maybe you're already somewhere over here, right? If you're the nearer you are to the limits, the lesser the margin you have lah, in a certain sense. So I hope I didn't confuse you, but yeah. So similarly for the gain and the phase, it takes on this analogy. So the distance between where you are and the limits is actually the margin. Okay, I may be wrong, but let's continue first and see how it goes. Alright.
This is sort of like our safety net in the design, and can also answer the question of how stable is stable. Designs that have less margin can be considered less stable in a sense, because smaller variations in the system could cause instability.
So as you can see, less margin equals to less stable. So if your system is, so you have a larger margin over here, okay, compared to here, right? So definitely this back dot is much stable than this one. So this one has a lesser margin, right? Has a lesser this. So this is what it means, lah. Okay.
Now, I have a real quick side note. Now, I don't know if the margins on your paper are derived from the same word, but if you think about it, that's the part of the paper that you aren't planning on writing in, but you could use before you run off the edge and draw on your desk. In case it wasn't clear, in this analogy, drawing on your desk is having your system go unstable. So now you might wonder why we
So
designed
this is just saying that this paper, the silhouette of the paper is actually the margin. If you cross the margin, okay, sorry, it's actually the limits. Okay, if you were to cross this limit, you're actually unstable. So this the distance from your writings to the limits is actually the margin. So how much margin left before you become unstable, it describes that. So definitely this margin analogy is being applied for the gain and phase margin. So this is what it means throughout.
a system with margin built in the first place. Well, usually when you're designing a control system, you're doing so based on a model of the system with mathematical equations, or you're testing a control system on physical hardware under known conditions and then making some assumptions about the way that your physical system will behave beyond the test environment. And the problem is that things don't always behave the way you expect. For example, if you're building a brushless DC motor controller, gain and phase errors can come from multiple places. A few include the rotor inertia could be different than what you predicted, so that the commanded torque generates a slightly different acceleration than what you wanted. Maybe you find out that the voltage regulator is sensitive to temperature changes, so when you run the motor in hot weather, the power to the motor isn't what you expected. Perhaps the lubrication on the bearings generate more friction than you expected, and so the motor is slower to respond to commands. Or the digital computer that is pulling in sensor readings and generating commands runs a few milliseconds slower than you thought it would, and adds more delay into the system. All of these variations
So all this variation is actually things that you may not understand. So therefore you want to keep a safe margin. Okay, you want to keep a safe distance from the limits. So if you want to design, make sure you design somewhere away from the limits, so that you can actually have rooms for whatever. Let's say you're here, but the with all this, unforeseen circumstances, your actual systems may be here, right? So that you need a certain so called an extra amount so-called reserve in order to prevent anything from going unstable. So definitely you don't want your system to be around here, right? Because if you cannot foresee the rest of the thing, you may actually the actual system may actually fall across the limits, which is very unstable, right? So this is what they're trying to say.
Plus others can occur when you operate your controller in a real system. We call these process variations, and typically you want a design to be robust to them. You can't know your system perfectly, therefore you have to build in margin to account for it. So the bottom line is that you'll have uncertainty in how these process variations will affect your system. And the more uncertainty you have in your system, the more margin or more stability you should design in. But to really understand stability margins, we first need to understand what makes a system unstable in the first place.
Okay, so you hold on a while. I think we can still continue. Later on I'll stop the video.
If you have a system G of S, then it's unstable if at least one pole or a root of the characteristic equation is in the right half plane. But as I've explained in my video,
meaning if your transfer function is let's say B of S, right? B of S. So if let's say your pole, okay, it's if you know that you cannot cross over the right half plane, right? If any of your pole is in this plane or zeros in this plane, is actually unstable. Okay, I don't know whether it is zero also, but in this case, if you have any pole in the right half plane of a S-plane plot, okay, the typical when you want to plot your root locus, you plot your poles and the zeros, right? This is all the X-plane. So typically your denominator must not be s minus 1 or s minus 2. Typically every time you see your transfer function, you always have s plus 1 plus 2, something like that. So this is just the thing. So you don't want so it is unstable if your poles are in the right half plane, right? So if your poles is in the right, so in this case zeros can be in the right half plane, but yeah. So let's cancel this first. So you just need to know that if the poles is in the right half plane, it's very unstable. That's all. Okay. So later he'll explain.
The stability of closed-loop systems, it's sometimes impractical to design a system in closed-loop form, and you're much better off designing the open-loop system and then using tools like Bode, root locus, and Nyquist plots to assess the closed-loop stability and performance. So let's talk about what characteristics of the open-loop system creates an unstable closed-loop system. Let's once again start with an open-loop transfer function, G of S. And when we close the loop around this system with unity feedback, the closed-loop transfer function becomes G of S divided by 1 plus G of S. So for the closed-loop system to be unstable, we'd need a pole in the right half plane. But we can also think about it this way. An unstable system has a gain of infinity because unstable systems will grow unboundedly, which is infinite gain. In order for this transfer function to have a gain of infinity, the denominator needs to go to 0. And for that to happen, G needs to equal minus 1.
So in this case, we need a pole in the right half plane. So in order to make this unstable, you will need a pole in the right half plane, right? So in other words, it's just a play of word. So in this case, so he comes to here. So if 1 plus G of S is equals to 0, the whole system becomes infinity, right? So therefore, if you have a pole in the right half plane, okay, it will be unstable. Okay, then therefore it goes to infinity. And then you take this is actually the characteristic equation. And then if you were to take this out, 1 plus G of S equals to 0. So in this case, this is a undesirable case. If it's equals to 0, it will go to very instability. So therefore, you want to find the most unstable margin, right? I mean unstable limit. So in 1 plus G of S equals to 0, so you just bring this 1 over here. So G of S equals to minus 1, that's all. Okay. So this actually proves the previous video that I talked about how we derive this. And yeah, and then yeah.
Aha! So we just need to keep our open loop system G of S away from minus 1, and our closed loop system will be stable. The minus 1 point should sound familiar to you, because it's the exact same -1 point that you're also trying to avoid on a Nyquist plot. And the gain of a -1 system is 1, or 0 decibels, because it doesn't scale the input by any factor. And the phase is minus 180 degrees because it flips the input upside down, which is a phase shift of half of a wavelength.
So in this case, when it's unstable, right, your gain, you didn't amplify it, but rather than you have a phase of minus 180 degrees. So you're turning the whole system upside down. So I don't know, so let's see first.
So the -1 point can be represented by 0 dB gain and minus 180 degrees phase. And if any one frequency across the spectrum hits that point, the entire system is unstable. So we need to...
So this is why he says that although your gain equals to didn't change, but your phase angle shifts totally. So I can't explain why gain equals to 1, because as you can see, unstable always they go infinity, right? So I think it's because yeah, perhaps you didn't amplify things, but rather than, since the phase angle changes, everything gonna change. So that's why it goes 180 degrees different. Okay, whatever. So this is just the simple theory behind why -1 is unstable. So this is the meaning in there. So 0 dB is just nothing changed lah. Okay, you didn't input anything. So the gain is equals to 1 times the transfer function itself. You didn't change anything.
Stay away from that point at all frequencies. So now we can finally quantify what we mean by margin. Margin tells us how far away from the -1 point, or 0 dB and minus 180 degrees phase, we really are.
So therefore this gain margin is actually, this is the limit, right? So this limit is actually -1. And then how far away from this -1 is, you know. And then if I may be wrong, but still, if you are around, but if you cross across, let's say you have a radius 1 circle, right? You have, maybe this is the origin, and you have a radius 1. Whatever system that is within the radius 1 is safe. Okay, so within this region is safe. But however, if you cross over to this side, is considered unsafe. Okay, so this is the thing. Okay, I may be wrong. So yeah.
So now we can finally talk about the Bode plot. And
I think we shall stop here because it's not talking about Bode plot anymore. We're talking about Bode plot. So this is just a brief intro to gain and phase. So in the next video, because since you already know -1 and the phase shift minus 180, because you're shifting 180 degrees. Okay, you're shifting over here, right? So therefore, with this understanding, later we will talk about the meaning behind our phase angle. I mean our gain and phase margin. As you can see, it's 180 degrees, and you know that thing. So let's say, yeah. So bye bye.